Okay, in this problem, a horizontal circular pipe is visible up to the point where it travels through a wall. The engineer can't see the pipe on the other side of the wall, but she can read a pressure sensor mounted over there, claiming that the fluid on the other side of the wall is lower than on the side she can see. Is the diameter of the pipe on the other side of the wall larger or smaller than the diameter of the pipe on the visible side? Assume that the total energy and head is conserved between both sides of the pipe and that there are no head losses. So, what this problem wants us to do is utilize Bernoulli's equation. And that's the first thing we need to recognize from what it's telling us. So, it calls out total energy and head being conserved, and it notes that the pipe is horizontal and that a pressure reading is provided. So here's what we can do first. Let's search out Bernoulli in our civil reference manual, and let's write out this equation real fast. So the first thing would be Z1 plus P1 over gamma plus V2 over 2G equals Z2 plus P2 over gamma plus V squared 2 squared over 2G. So in this case, this side of the Bernoulli equation represents the visible pipe that we can see here, and this side represents the invisible side on the other side of the wall. So the problem is essentially asking us if the area or diameter of the pipe specifically, but if the area on one side is bigger than the other. So there's a few things we can do to simplify this out immediately. The problem notes that the pipe is horizontal, so we can eliminate our elevation head from Bernoulli immediately. That leaves us with the pressure head and the velocity head. So we have P1 over gamma plus V1 squared over 2G equals P2 over gamma plus V2 squared over 2G. Now there's one more thing we can tell from looking at this. It's noted that the fluid pressure on the far side of the wall is lower than on the side that the engineer can see. So let's say, just for reference sake here, that P2 equals 1/2 of P1. That might make it easier to think about for some people. So what we can tell is, since P1 is greater than P2, if the total head's going to be conserved, which is mentioned here, then V1 squared over 2G has to be less than V2 squared over 2G. And to take this logic one step further, let's take our Q, which is going to be constant through the pipe, equals A1 times V1 equals A2 times V2. So if we know that V2 is going to be greater than V1, ostensibly A2 has to be less than A1 if we're going to have the same constant flow rate through the entire pipe. So therefore, the answer to this problem would be that the diameter of the obscured pipe is going to be smaller than the diameter of the visible pipe. Since A2 is going to be less than A1, the diameter on the other side is going to be less than the diameter on the visible side. So that's all it takes to solve this problem, is an understanding of Bernoulli. If you want, we can also just look at this by plugging in real numbers if you're the kind of person who has trouble thinking about this just in terms of terms. So let's come up with some random numbers here. We're going to take this first equation again, and we're going to start applying terms to it. So we'll say that Z1 equals 1 foot, and P1 will be equal to 5 feet per second squared, because don't forget that a pressure is a force over an area. So, oops, pounds, not feet. Saying it out loud helped me catch that. So the gamma in this case is the specific weight of water, which is going to be 62.4 pounds per cubic foot. And oh, I made another mistake up top. I was thinking about velocity for some reason. So it's pounds per foot squared over pounds per foot cubed, which is how it's going to end up with a foot unit at the end to match up with this one. And finally, we'll say the velocity is also 5 feet per second squared over 2 times 32.2 feet per second squared, which is our gravity. General note too, if you don't have this term memorized, it's a good idea to do it, but also gamma is given in chapters 1, 3, 6, 7. But yeah, memorizing 62.4 pounds per cubic foot will save you a lot of time and hassle. So that's going to be the equation on one side. And let's move this down and make this a little easier to see. Sorry that we're moving stuff around. Okay, so we can also tell that, so this is our one side of the terms over here. This is going to be Z1 plus P1 over gamma plus V1 squared over 2G equals Z2 plus P2 over gamma plus V2 squared over 2G. So let's make up some terms for this side. We agree that this is a horizontal pipe, so this is going to be 1 foot as well. The pressure we said is the reading on this side is less than the reading on the other side. Let's just claim it's half. We don't know, and it doesn't really matter. Anything we solve out for on this side is going to work out the way we need to at the end for the area and the velocity. Over 62.4 pound cubic foot. And then the velocity is what we need to solve for here. So that's V2 over 2 times 32.2 feet per second squared. So solving this out, would you be able to just run the calculations for this side and then subtract out this term and this term, multiply by 2 times 32 and do the square root. And if we do all that, we will see that V2 equals 5.25 feet per second. And this is going to be greater than V1, which we said was 5 feet per second. So from there, you could go back to looking at this. So you could just come up at that point with a arbitrary flow value and divide by the calculated velocity on either one, and that will give you the respective areas for each side of the pipe as well. So yeah, coming up with fake terms is probably not the recommended strategy. Fake real numbers to plug in and check on the test, just because it's going to take a lot more time. So if you can work through with just the equation like we did up here, that's going to be your best bet. And then using your understanding of these equations, such as Bernoulli and the equation for flow, using those two will be a much more efficient way to solve a problem like this. Okay, that's it.